secant line. That's Rolle's theorem. Okay, now in this case, the two intercepts are right there. So there's somewhere in between them. Actually, this one opens up where there's a horizontal tangent. Not necessarily right in the middle, but somewhere in between them is the idea. Any feedback or questions on that?
Nope, that makes sense.
Okay, it doesn't, and you don't even need to know that. You just need to know, okay, I got to take a derivative here. Could you give me the derivative of this, please?
Yeah. Two x minus 1.
X minus 1, good. We set that equal to 0. Solve that for x, please.
Half.
X equals 1/2. So the idea is that at 1/2, there's a horizontal tangent because the secant line, those two intercepts, you know, you can think of the x-axis there. There's somewhere in between, what do we say, -1 and 2, where there's a horizontal tangent.
Okay. Seems easy enough.
All right. Yeah. I mean, it's really not
Yeah.
that big a deal. It's just they give it a name and you'd say, oh my gosh, what's this name? Doesn't really matter what it is. It's all right. What's the next one you'd like us to look at?
11.
All right. So there is some language in questions 11 through 23. You have to decide if you can even apply Rolle's theorem. This is where I think math kind of gets really unnecessarily complicated because they give you, I'll just snip this in here. They give you some instructions, but they don't, and these are completely correct. It's just like, it's like overwhelming. It's like, okay, the first one says the function is continuous on the closed interval. So it just means, is the function continuous? This is a quadratic. Yes, it's continuous. Okay. Because you might get a test question where you think you can apply it, but you can't. And I'll try to look for a problem where you can apply it. We'll see if they actually come up.
Okay.
Differentiable is related to being able to take its derivative. Yes, you should be able to take its derivative. And it's because it's continuous, it has a nice derivative. Like 1 typically leads to 2, but not always. Like here's a function that's continuous but not differentiable. See, I can draw it without lifting my pencil, but it's not differentiable because the slope from the left is not the same as the slope from the right. This is called a cusp. You can also have corners. Those are also not differentiable. Few things there. And then this is the key one. This is the one you're really looking for, is the evaluation of the endpoints the same. So you actually do need to find f of 0 and then f of 3. And you don't want to just assume that they're equal, even though they probably are in almost every problem you'll do. But that would be my recommendation. So if you want to go ahead and calculate those at the endpoint, please, and let me know.
So just solve like f of 0
Yeah.
and f of 3.
Yep.
Okay.
Yep. Back in there.
Well, f of 0 is just 0, and then f of 3 is also 0.
Good. Okay, so we've satisfied them all. So what it says again, and it's not really working out great because we keep getting zeros. Like yeah, that means that it's 0 and 0. Like there's a horizontal tangent. So the graph, which let me take a look at the graph again. So this time it opens down. There's a place where there's a horizontal tangent, but it doesn't have to be horizontal. It really could be, you know, and there could be more than one. Like there's the secant line. It could be that the curve looks like this and then like this. There's actually 2 places where it's got the parallel slope. Just so happens that we're getting ones where it's 0. So the next thing is to take a derivative of this. Could you help me out with that, please?
Yeah. Negative 2x plus 3.
And so you set that equal to 0. And you end up getting x equals 3/2. And you check to make sure it's in the interval. Like, is it between 0 and 3?
Wouldn't it be negative 3/2? Because you bring the. Or no. Yeah, okay.
Yeah, I mean, it's
yeah.
okay. It's sometimes better if you let the student kind of work through that.
Yeah,
I do
no, I
make
had it
mistakes.
written. I wrote it wrong. I wrote subtraction instead of a plus. That's why. But yeah.
So it's in that interval. I mean, it's happy to it's not always right in the middle. Like, that's the problem, is you might be thinking, oh, it's always in the middle. No, these are textbook problems. So the answer here, the C that they're looking for, is 3/2, and I didn't make that clear. Like, this is A, this is B, and that's C.
Okay.
That's the next question you'd like us to look at today.
29.
Okay. The part A, not calculus. It's just evaluating the function at the two endpoints. So
Right.
that you throw in a ball up. It's what the graphically looks like, and I really think that they can emphasize the graphs more than anything. Goes up, comes down. You want to find f of 1 and then f of 2, and I'm guessing they're at the same height there. So if you could evaluate that for us, please, and let me know what you come up with.
F of 1 is 38. F of 2 is also 38.
There's actually this classic problem in physics where you have the goalpost over here, and you kick a ball and it goes in, but you don't know whether it went in on the way up or the way down. And that's kind of where this comes from, because you don't know that it's at the same height, but you don't know whether you're on the way up or the way down, basically. So that's it for that part. The next thing to do in this problem is to, I believe, take a derivative, or let me put that up here. So according to Rolle's theorem, let me answer part B. So since these are the same height, the secant line is horizontal. I keep saying secant line. If you remember from geometry, a secant means it hits the circle twice.
Yeah.
Tangent line hits it once. So it means that there's a horizontal tangent between them. That's what part B is asking here. It's like, what do you know? Well, you know that at some point the derivative f prime of some c, and your c is between 1 and 2, like there's some number between 1 and 2 is 0. So again, like a lot of words and stuff to just say, take a derivative and set it equal to 0. So if you could take a derivative of that for us, please. Let me know what you got.
Negative 32t plus 48.
Okay, so if you want to set that equal to 0 and solve that for me, please.
Three halves.
Yep. That's your C. Your C equals 3/2 or 1.
Yeah, that is so much easier than just like the problem makes it out to be.
Yeah, and that's where I wish I could, so I got a friend who does physical therapy and he's not on insurance, but you can go to him and get fixed in one session. It's kind of the same thing here. Like you don't need, you know, a lot of help. You get the right help, it goes pretty quickly.
Yeah, yeah. Can we do 31 mean value theorem?
Sure. So the mean value theorem, it's got another set of things here, and it's saying that kind of the same deal here. So you actually, maybe I'm sorry, I didn't misspoke. Some of the things I was saying about the Rolle's theorem are actually for the mean value theorem. So the mean value theorem, Rolle's theorem, let's get back up. Rolle's theorem does require it to be horizontal. So this is not Rolle's theorem. This is the mean value theorem.
Okay.
And then, so the mean value theorem is where it could be, yeah, like this at an angle.
Okay.
So it's essentially the same thing. You end up evaluating the two endpoints, but this time the slope isn't zero. So let me snip this in so you can see it. Okay. Continuous, we talked about the differential, talked about that. So this is the secant slope, and it's the average rate of change. You've seen that a bunch in your math classes. Basically, there's a place where the derivative, the tangent line, has the same slope as the secant line. So we'll do an example or two. You said number 31.
31. Yeah.
Oh, and this is a picture. Okay. So let me grab the picture. It's probably good to do this graphically to start. The idea is you draw a line from A to B. That's the secant slope. Okay. And then there's at least one place, and here there's actually two, where there's a parallel and a parallel slope. And that's what you're trying to do. Are you okay?
Yep.
Okay.
Sorry, the website for my like schooling just crashed. So I was trying to pull up the questions again and it was just like wasn't working, but I got it up again. So we're good.
So the idea is, again, that whatever the slope of the secant line is, there's a tangent, at least one tangent, could be more than one, could be an
Right.
infinite number of them, not infinite, but there could be a countable number of them that are between. And I'm sort of guesstimating my lines here. I mean, I'm not very good at it. Plus, there's a picture of a picture
Right.
through a screen.
Yeah.
Check the answer. But you can do this analytically, meaning like we've been doing. You take derivatives and set them equal to this new slope. Hopefully, you've got another problem queued up for us to work on for that.
Let me check. I believe I do. And that would just be like one that has like actual like numbers on instead of just a graph, right?
Yeah, exactly.
Yeah, 37.
37. Okay. So they give you the graph, but let's just look at it like we don't have the graph for the moment.
Okay.
Because this you're not gonna get a graph and you can
Yeah.
look at it if you want, but okay. So they'll tell you something like x equals -1, x equals 2. So we need to evaluate that. So you'd find f of -1, which you can see from the graph is 4, and f of 2, which equals 1. So now what you do, the next thing this is the average rate of change. It's f of b minus f of a over b minus a. So it's a slightly different notation, but this is a, this is b, this is f of a, and this is f of b.
Right.
It's the slope formula. It's
Yeah.
y2 minus y1 x2 minus x1. It's 1 minus 4 over 2 minus a minus 1 minus 3 over 3 equals -1. Okay.
Yeah.
So that's the slope. So instead of that being 0 like it was in the previous problems, we then now take a derivative that's minus 2x. And this time, instead of setting it equal to 0, we set it equal to -1. That's the difference. That's the main difference between Rolle's and mean value theorem, is you set it equal to.
Okay.
Okay. That ends up being x equals 1/2. And you have to make sure that that's between the two numbers. The other reason is it just checks your algebra. Like, is 1/2 between -1 and 2? Sure is. And there you have it.
We do 42.
Okay, so you're supposed to do check all the boxes. Like, is it continuous? Is it differential? You also have to find f of 0 and f of 1. Okay, so I'd like you to do that for us, please.
Okay. F of 0 is 5.
Okay.
And f of 1 is 12.
Okay, and these don't have to be the same this time. That's a key difference between, for the mean value theorem, they don't have to be the same.
Okay, so for Rolle's theorem, they have to be the same, but mean value theorem, they don't.
That's
Okay.
right. All right, so let's see here. So again, you got to do this whole f of b minus f of a, 12 minus 5 over 1 minus 0, 7 over 1 equals 7. So that's what you're going to set the derivative equal to. So you got to now take the derivative, 3x squared minus 6x plus 9, and you're setting it equal to 7. Not 0. Why don't you try solving that? I'll be right back with you.
Yep.
So if you're not sure, don't remember how to solve it, you definitely want to move everything to one side. And this ends up factoring 3x minus 2, x minus 1.
Yeah.
No, that doesn't work. Sorry, the 1 goes in the other. That doesn't factor.
Yeah, that's what I was gonna say, is like I didn't feel like it was factoring out properly.
So it's possible. Do you have the show solution on this one? There you go.
Yeah, let me check.
It's 42, so it doesn't look like it'll be there. But you would let me just graph it and I'll
Yeah, 42 does not.
yeah. So this is a quadratic formula problem, which
Yeah.
means I mean it's fine. It's just another like little wrinkle, little addition to
Right.
this. But let me just double check here with some other things I've got handy. 3x squared minus 6x plus 9. Just make sure you're pretty confident on your answer here. So I didn't even check. The first one's definitely 1. So it'd be 1 minus 3 plus 9 plus 5. I'm only just checking. So I get 14, 11, 12. Does that look good? Yeah. 3x squared minus 6x plus 9 equals 7. Yeah, so this has you gotta use quadratic formula for this.
Okay.
And solutions ends up being 1 plus or minus square root 3/3.
Yep.
Something to think about.
Yeah, I'll just keep that on my reference sheet so that I have it just in case. And
All
then
right.
we can go to the next chapter, which is 3.3, and it starts with the number 3, but using a graph.
Yeah, so let's grab the graph and so the challenge here, the challenge really is there's rules for the original function f, and then there's different rules when your graph is of f prime.
Okay.
And what happens is students mix them up. Naturally so, because it's two sets of rules. This is f, this is the original function. So the following applies to f. Okay, so I'll just move this down. So if the interval is, so it's increasing when it's going up and to the right. Okay,
Right.
so I'll show that here. It's increasing all the way, and it's your x values. It's from 0 to 6 that it's increasing.
Mm-hmm.
It's also increasing from 8 to 9. Okay.
Yep.
It's decreasing if it's going down and to the right. So do that in blue here. That's from 6 to 8. That's from 9 to 10. So that's A and B. So that's A is increasing, B is the decreasing.
Oh, perfect.
But
Okay.
that only applies when you're given the graph of the original function, because you will get a problem. Well, typically you get problems where you get the graph of the derivative.
Okay. And then we do number 6. It's, it has a graph
Sure.
also.
Sure. Yeah, so let's do it without the graph, because that
Okay.
is kind of your problem here that you're going to get on the test or quiz.
Right.
All right, so here's what you do. You first take a derivative. So go ahead and give me the derivative, please.
2x minus 6.
You set that equal to 0 and x equals 3. Okay, so that is a critical number. Now there's variations on how you do this. I always make a sign chart on the number line. So I put that critical number right on the number line. I don't care where 0 is. I just care where that critical number is. It does go from minus infinity to infinity. And then you need what are called test points. Okay. Test points. So you're testing, there's windows, there's regions here. There's a region from minus infinity to 3 and 3 to infinity. So I draw those here separate. So like 0 is a good one, and then maybe 5. Okay. I try to keep those numbers away from the graph here, this number line. Sometimes you see tables, charts, but I think this is pretty simple, straightforward. So where do you test these points? In the derivative. Very important. In the derivative.
Okay.
In the derivative. Because this sign chart is for the derivative. So when you put 0 back into 2x minus 6, and this is where students, they focus on the number instead of the sign. This is a sign chart, not a number chart. We don't actually care what the number is. We just care whether it's positive or negative. 2 times 0 is 0, 0 minus 6 is negative 6. All I care about though is that it's negative. Don't care what it actually is. And you'll see in the more complicated problems that that's really helpful because you don't have to actually get the result. 5, 2 times 5 minus 6 is a positive number, like that. So guess what this tells you? It tells you that it's decreasing where it's negative and increasing where it's positive. Now let's go to the graph. Now that we have a graph, not a sign chart, and let's see that it's consistent with that. But before I do, any questions on what I just said or anything you'd like me to clarify?
No, that makes sense. That was easy.
Okay, now let's go to the graph. Is it consistent? Yes, at three, there's a critical point right there. And so what's happening from minus infinity to 3? Is it going down into the right?
Yep.
Decreasing. Decreasing. From 3 to infinity, is it increasing? Yeah, it's increasing. So it's consistent.
Perfect.
So there's some rules here also to, and this is called the first derivative test, what we just did, first derivative test. If you go from minus to plus, that's a minimum. Minimum. So notice that we went from decreasing to increasing.
Yeah.
That's a minimum. If you go from plus to minus, that's a maximum. And if you go from minus to minus and plus to plus, it's nothing.
Okay.
These are kind of note card, cheat sheet, reference sheet stuff that you'll want to have. Any questions on that?
Nope.
So your answer though, like I didn't really like your full answer is that you want to say decreasing from minus infinity to 3, but in your case, it'll be a multiple choice. It'll say, decreasing minus infinity to 3, increasing 3 to infinity, or it might just ask where it's increasing or decreasing, and so on and so on.
Okay. Let's see. We'll do number 11.
Yeah, so this is a great, this is almost exactly like what we just did, right? It's different numbers, but exact same thing. So why don't you take the derivative, set it equal to 0, and test some points. So you want to take a derivative, set it equal to 0, get that critical point, and test numbers on either side here.
Okay, so x equals 1.
Okay, so there's your critical point. So you want to test something on the left and the right of it.
And so do I just pick any number?
Yeah, any number. Like I would test 0. 0 is always a good number. It doesn't have to get, you can get, it has to be a little bit away.
Mhm.
Again, you don't care about what the actual, you don't care what the actual result is. You just care that whether it's positive or negative.
Okay. So 0 is negative. 2 is positive. Okay, so when it's less than 1, it's negative, or yeah, negative. And then when it's greater than 1, it's positive.
So you'd want to say, and here's how you answer it, or it be written, decreasing minus infinity to 1, increasing 1 to infinity, like that.
Okay. Okay. Let's see. Can we do 19?
Sure. This is exactly, I mean, it's
Oh,
exactly the
is it?
same problem.
Oh, okay.
It's,
Um,
it would be good for you to try if you have any questions, but
okay, can we do 26?
yep, so the only thing different about this one is just it's a harder derivative. So this is a 26 is a product rule derivative, but
Okay,
within the product rule, it's a quotient. I'm sorry, a chain rule, not quotient, meaning over here on the right. So if your f is 8 minus x, and your g is x plus 1 squared. So give me the derivatives of f prime and g prime here if you can.
f prime is just gonna be -1,
Okay,
and g prime. Do x plus 2.
so it's 2 times x plus 1 to the power of 1. That's the power rule. And then you take the derivative of the inside function.
Yeah.
So the derivative of x plus 1 is just 1. So it's 2 times x plus 1 or 2x plus 2 if you want to expand that.
Yep.
So your derivative here is 8 minus x times the, and I'm going to leave it vector because that generally is preferred here, x plus 1 plus -1 times x plus 1 squared like that. And so you probably haven't done one that's algebraically complicated yet, but you need to factor out an x plus 1 from both. So you end up getting 2 times 8 minus x from the first one minus an x plus 1 here. And so it looks bad, but you just have to simplify it. It's 16 minus 2x minus x minus 1 and 16 minus 3x, or it's actually 15 minus 3x here. And then you could even go a little bit further and factor out the 5, so it ends up, or factoring out the 3, so it ends up being 3, 5 minus x here. And then you're setting that equal to 0. So any questions on, derivative or algebra manipulation here? I know we talked initially about not skipping steps. Anything here you need some clarification on?
No, that makes sense.
Okay, so you set them each equal to 0, x plus 1 equal to 0, 5 minus x equal to 0, x equals -1, x equals 5. Those are your two critical numbers. So this time on your sign chart, there's two numbers to try, okay? So your test point, again, I strongly recommend that you keep them away from the actual number line,
Yeah.
0, 6, and -2. Okay. And you're testing them in the derivative, specifically in the factored form of the derivative. Because if you think about the way signs work, when you're multiplying, a positive times a positive times a positive is positive. If you have one negative and two positives, that's negative. There's these things you can use. So, but if you don't like that, you just put the numbers back in here and you get your answer. So start with 6. 3 times 7 times -1, whatever that is, but it ends up being negative. I know as a student, you want to get the number, but you actually only care about the sign. 0, 3 times 1 times 5 is positive. The last one here, -2. 3 times a -1 times a positive ends up being a positive there, which, yeah, that is right. Okay. So this is that case where you have two positives, and that means there's no min or max here, but there is something going on here at 5 because it goes from positive to negative. I don't think it's asking for that. Let me look back one more time. find the critical numbers where it's increasing or decreasing. So we found the critical numbers, -1 and 5. And right, so that's the critical numbers. Now, increasing or decreasing, you can just say increasing from -infinity to -1, comma, -1 to 5. So notice you can't just overlap these, because at -1, it's neither increasing nor decreasing. Does that make sense? Like it's a horizontal tangent like we're talking about.
Right.
It could be going the other way, but because it's plus to plus, we know it's this one on the left here. It's not a great place to be, but that's what it is. I mean, so, and then you'd say decreasing from 5 to infinity.
Perfect. Okay. That makes sense. And then can we do 42?
Sure. Okay, yeah. So why don't you take a derivative at 42?
Yeah.
41. Okay, 42. So why don't you take a derivative for me, please, if you don't mind. The first one is a product rule to help you out here. Sin x, cosine x, that's a product rule derivative.
Okay. Cosine 2x.
So yeah. So your f here is sin x, and
Yeah.
your g is cosine x. So what's the derivative of sin x?
Cosine x.
Cosine x, and what's the derivative of cosine x?
Negative sine x.
Sine x. Good. Okay, that part's good. So you're pairing them up here. So it's sin x times negative sine x. You're multiplying
Right.
plus cosine x times cosine x. So the just a reminder here, it becomes sine squared x plus cosine squared x, and you're setting that equal to 0.
Right. Okay.
So now let's set it equal to 0. That's a little bit more difficult to do. You you have to set these equal to each other. So it's where does sine squared x equals cosine squared x. Basically, it's where does sine equal cosine on the unit circle, which I'm surprised it doesn't give you a tell you to go from like 0 to 2 pi. Let me just quickly graph this because it's again, the graph tells you so much. This whole course can be done with just a graphing calculator. Why doesn't it like that? All right, let's put that in parentheses. Okay. So yeah, the thing is that this graph oscillates forever. I mean, like, I don't know why they're doing that, but the thing that is important here is that sine is equal to cosine at 2 places on the unit circle. Here at pi over 4, and then at 3 pi over 4. So this basically repeats, but we can just look at it from pi over 4 to 3 pi over 4. Okay. And this is where when you test points, you've got to remember your trig. Like, okay, so pi over 2, maybe, maybe 0, maybe 2 pi. But you got to pick some points, and you got to be careful that you pick ones that, or maybe you just do pi. Pi is probably even a little better there. Okay, so you're going back though to the derivative. You're going back to this line here, not the one where you set them equal, which could be a little awkward. I don't know how comfortable you are with your trig here, but it's you're testing them in y equals. Let me just rewrite this here: cosine squared x minus sine squared x. Okay, so at 0. At 0, the cosine of 0 is 1. The sine of 0 is 0. So this ends up being 1. Cosine squared is 1. 1 squared minus 0 squared is 1, or positive. And then from pi over 4 to pi over 4 pi, cosine of pi is negative. Sorry, I did pick a bad point. Sorry. Sorry, I'm not doing this right. There's more critical points because of the fact that it's squared. You also have these ones to consider. So there's also this one over here at 3 pi over 4. This is 5 pi over 4 and 7 pi over 4. So we got to back up in a sign chart here. There's a lot to this one. So I'm just going to do it from 0 to 2 pi. That's kind of this thing oscillates forever. So you got pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, like that. Okay. So you got to test. That's where it gets really hard. You got to know what's going on, like in this region of the unit circle. So it ends up that cosine the x is bigger than the y here, but you're squaring these numbers. So it's almost better if you know what the graph looked like to do this. Let me try to illustrate that here with this. Okay, so here's the graph of this thing. You kind of shape it so you can see that it's increasing, decreasing, increasing, decreasing, increasing. Like these line up with these kind of places.
Okay.
To do this by hand, you have to be comfortable with like what the actual values are here, and then what happens when you square them, which is, I think, very difficult to do. I'm sure this was probably designed as a calculator question, which means you shouldn't object to graphing these like on your test.
Okay.
To figure out where that window is. So
Okay.
okay, maybe time for another question. I know we're coming here to the close of our lesson.
I think that was the last one. I think I'm good.
Oh wow. Okay. So we got a lesson tomorrow at 4, and then Thursday at 11.
Yep.
So I'll see you then. We go ahead and stop the recording.